In this video, we're going to talk about one of the most important theorems in all of calculus, the fundamental theorem of calculus. You can probably imagine that with a name like the fundamental theorem, this is going to be really important. To start, let's suppose that little f is integrable on the interval ab, and let's define a new function also on the interval ab. This new function takes in a point x in the interval and outputs the integral of f from a to x. If we draw a picture of a typical function, we can visualize what f is doing. Since the integral is the area under the curve, for each x, big F of x is the area from a to x. This is a function with which we need to get familiar, as it's about to show up a lot. Without further ado, let's introduce the fundamental theorem of calculus, sometimes called FTC for short. The theorem consists of two parts. Both are related, but also slightly different. In the first case, we assume that f is integrable on the interval ab. Now, looking at the function big F of x that we defined above gives us two results. The first is that big F is guaranteed to be a continuous function. But we can say more, since in fact big F is differentiable anywhere that little f is continuous. In effect, the function big F is guaranteed to be an antiderivative of little f. For the second part of the FTC, we again take little f to be integrable, but now let's suppose that big F is a continuous antiderivative that is differentiable at all but finitely many points in the interval ab. Then, we can actually evaluate the definite integral of little f by evaluating big F at the endpoints of the interval. You should definitely pause the video and look at these statements and become comfortable with them. The first result tells us that integration gives us an antiderivative, while the second result tells us that we can use antiderivatives to evaluate integrals. The second part of the FTC is going to be used more often than the first, so let's start by seeing this in action. Let's integrate the function x squared minus 1 on the interval -2 to 2. Now, graphing this isn't necessary at all to solve the problem, but I want you to see the function. It's definitely not one of our standard shapes, like a triangle or a circle, and some of it is beneath the x-axis while some of it is above. We would have no idea how to do this without the FTC, but with the fundamental theorem, it's not too bad. According to the theorem statement, we first need to find an antiderivative for x squared minus 1. We've got some experience doing this, so let's take big F of x to be x cubed over 3 minus x. Applying the FTC, we can evaluate the integral by calculating f of 2 minus f of -2. Now at this point, it's just algebra, so we'll plug through the calculations pretty quickly. There's some nice symmetry here, owing to the fact that x squared minus 1 is an even function, but we're going to relegate that to later. So after all of this, we end up getting this pretty nice answer of 4/3 out. Awesome. Now, we know that antiderivatives aren't unique, so a good question to ask at this point is what would have happened if we had used a different antiderivative? Well, let's try it. Let's take big G of x to be the same antiderivative as above, but let's add 100 to it. Using the FTC in the same way as above, we compute g of 2 minus g of -2. Now, the algebra ends up being similar, but we get this extraneous constant of 100 showing up everywhere. So I'll run through some simplification, but I'm also going to regroup the terms in a clever way to help us see what's going on. The first set of brackets is the same result that we got above. The second set of brackets are the constants coming from g of 2 and g of -2. The constants thus cancel each other out and give us the exact same answer as above. Now, of course, there's nothing special about the number 100. Taking g of x to be f of x plus c, and applying the fundamental theorem, we'll see that the constants cancel each other out, giving us the same answer regardless of which antiderivative we use. Now the other part, the first part of the fundamental theorem, is less frequently used, but let's see it at work. Here's a nasty function, defined in terms of the integral. But it is a function, since if we were given a value of x, we would integrate ln t minus 1 divided by t on the interval 2 to e to the x. So let's find its derivative. Our problem is that we can't directly apply the fundamental theorem. Per the theorem statement, the upper bound of integration needs to just be x, not e to the x like we have here. But let's start with what we do know. Let's define a function f hat of x to be the same as f above, but integrating from 2 to x instead of 2 to e to the x. So the only difference is the upper bound of integration. As I said before, we do know the derivative of f hat. It's just the integrand ln x minus 1 divided by x. Now the key is relating f hat to f, and the way that they're related is that f of x is f hat of x evaluated at e to the x. If you don't see this right away, I want you to think about it. If we plug e to the x into f hat, what changes? Well, the upper bound of integration changes from x to e to the x, and that's exactly f. Thus, we can differentiate big F by applying the chain rule, giving us the following. But we know the derivative of f hat, so we plug everything in and get x minus 1 as our answer. So the fundamental theorem of calculus allows us to relate the area under the graph to the computation of an antiderivative. And that's a big deal, since now we can compute non-trivial areas.